Hello everyone, and welcome to another episode of Solving Advent of Code in Rust and trying to learn Rust in between. I'm Roberto, and we have...
Luciano.
Thank you everybody for following along. If you never did Advent of Code is a challenge that is published around the Christmas time every year. We are working on the last year ones, and there are 24 challenges that you can find on adventofcode.com. Yay, there. We are publishing all our code in a GitHub repository. It's a GitHub repository, but it's also on GitHub. We have this banner, and we have a YouTube channel where you can find all the published past recording on what we did. Last time, we were working on exercise 20, I think, part
20,
1, and
yeah.
we were able to do it. We were not expecting to be able to do it, but we were able to do it. We did it, and we found the four corners of our image. Now, what we have to do today is going on, compose the full image, and looking for something in the full image. How do we do this?
Do we want to quickly discuss that PR first and maybe get it merged?
Oh, he's right. You're right. Okay. Do you want to share the screen if you have it ready?
So I'm gonna show very quickly. By the way, thank you, Tommaso, for submitting another amazing PR. I think you are winning some prize now.
Yeah, Oktoberfest t-shirt probably.
Also that, yeah. So basically, I think the idea was, first of all, to make the tile using arrays rather than vectors, using const generics. So basically, this will be in real life a tile 10 because we know our cells are like 10 by 10. And this time we will create a cell. All the cells will be array of 10 by 10. Basically.
We thought of this approach last time, but we discarded it because for us it was too complicated.
And then the other thing that Tommaso was suggesting is, this way when we use arrays, basically accessing the data is already a copy operation, so we don't need to do clone explicitly. And then there was another interesting thing that is implementing the from string for parsing the input, which is definitely a lot more idiomatic. And that's, I think, pretty much it. Everything else is just, now we need to instantiate as tiles 10 because we need to provide the number.
Also, it's accessing with the tiles of 0 in line 75, the new one.
Yes, because
now tiles is a container. No, how it works.
Tiles. Interesting. Let's see. Because here is not, it's a proper struct.
Mm-hmm.
So what is tiles 0 there?
I was the one asking it.
Tiles 0, is this tiles a list of
is
a table or something?
It depends on what unwrap is returning. Input parse unwrap.
So this parse maybe is returning
okay, self tiles. Line 65, the new of the pull request.
Mm-hmm.
Is returning okay, no?
This is the specific signature of from string, which will give you parse. But then the return type of this should be a self, right?
Yes. And self
so here, once you do unwrap, you should get tiles.
And the type tiles change the definition, or is still the same as before?
Tiles is...
Where is the
Wait a second.
The type.
Oh, because it's this one. Yeah, this is a single tile that didn't change, basically.
Mm-hmm.
It's just const generic now.
Okay.
While tiles is basically an alias for... Well, it's a wrapper type.
It's a wrapper, okay.
So it's not an alias. That's why we need 0. So that 0 is to access the actual hashmap.
Okay, so makes sense. I just wanted to understand why. Sorry.
No, it's a good question. I didn't notice. Good one.
Do you want to merge it now?
I think so, because I'm concerned that otherwise it will diverge too much.
If we do part 2 without merging before, we are going to
So
explode.
I'm gonna merge this, but meanwhile, if you want to explain our approach to part 2, I'll give you the board.
Yeah, I will try to explain the approach to part 2 because composing the image is a little bit more tricky. So just give me a second to share a Scali draw. Can you see it, Luciano?
Yes, I need to add it to the stream. Can you make it a little bit bigger somehow?
Good question.
Okay, that's perfect.
Okay, so let's go like this. Okay. Our final image, we know that will be an array of IDs. I think we used U16 for our IDs. Okay, let's not look at what I wrote because it's just wrong. 12 by 12, because we know that we have 144 tiles. The square root of 144 is 12, so we know that we have an image arranged in 12 by 12. This is an information that can be useful. And we know that we have the 4 corners. We take one of those corners, arbitrary, one of the 3 of them, and we say this corner is the top left. We don't care if it is really the top left. If it's not the top left, we will just have our image rotated in the wrong way or flipped in the wrong way. But this is something that we can address later. Also because in part 2, we also have to look in this image that we compose and looking for patterns. And we have to look for patterns that can be flipped, rotated, and so on. Right, Luciano?
Yes.
So in the end, if we go to an image that is flipped or rotated, it's just a matter of we don't care, basically, for the final result. Starting with a corner, we know that a corner has only 2 neighbors. The 2 neighbors will go in our array here and here. If we put the wrong one here, they can be swapped. If we put the wrong one here and we put this other one here, again, the only stuff that we can get is to have the image flipped on the wrong axis. Again, we don't care. So we arbitrarily decide what of those 2 is 1, 0, and which one is 0, 1. Now, we have this variable, and we can go in recursion at this point. We start with this scenario. Recursion, we work on this on this cell and this cell. Let's say that we go to this cell first. This cell first will have 3 neighbors, and we already know them because we have them in I think we have them in an array of neighbors, right, Luciano?
We have a hashmap of neighbors.
An
hash set for neighbors. So for every cell, we know which ones are the neighbors, basically.
Perfect. And we will only have 3 neighbors. But one of them will already be set. There will be this one. So we only have to fill 2 cells. Again, this come handy to us is to know that one of those 2 neighbors that we have to add, one will be a border. So will be, again, a neighbor with only 3 neighbors. And we can pre-compute an hash set of all the IDs that are borders for simplicity for us. And so we can already tell exactly which one will be here and which one will be here, because this other one will have, wrong tool, will have 3 neighbors. Then we go with our recursion, we have to do 2, 4, 5, 7. 2, 4, 5, 7, we can do this with recursion or we can do this with a stack. I'm just a little bit worried that passing around this structure in recursion, there are lifetimes involved, and I always get beaten by by Rust and recursion, so I'm scared.
Yeah, especially because we will have this mutable view which we are building. Yeah, so that might be tricky to do it in recursion.
But at this point, you do a stack. You start with a stack with 1, 1, 4, 7, 2, 4, 5, 7. You pop the stack on the left, you add on the stack on the right, and you go on popping on the left until the stack is not empty. So you go on like this until you have all the image. At this point, you have to do in your stack 2, 4, 5, 7. Again, you have 3 neighbors, but 2 of them are already defined. So you just have to write down the new neighbors. At this point in our stack, because if we choose to go with a stack, we will have 3 numbers, 4786, 4741, and 5475. And you go on like this. If the number is a border, you have to put a border. If on the right, if a number is not a border, you have to choose excluding what you have around. But the nice stuff is that when you are in an internal tile, let's say that we have a matrix that is only 4x4, so we can do all this stuff and getting to it faster. When you're getting here, you will have this defined, again this defined, because when you do this tile, you can have already the numbers here. And random number. Okay, this is not a valid tile. But when you have to do internal borders, you already have 3 of them setted. And so the only one that you have to set is the one by exclusion. And you go here. And here you have just another tile number. Also here, when you do this one, you will only have 1 number by exclusion, because you have 3 neighbors, but 2 of them are already defined, so you can only put 1 of them there. And you go on like this. The only tricky part here is when you get the top, this one, that can have 2 neighbors, and 1 go on the right and 1 go on the bottom, and they are, 1 will be a border and 1 will be something with 4 neighbors. So you have to do this if here, if the current tile is a border. Another stuff you have to keep track when you reach the 11th cell, when you are at the 11th cell, because the one on your right will not be a border at that point, but will be a corner, one of the 3 corner that are left. So there is a little bit of edge cases here to take in account, but it's doable. When you run out of tiles, it means that you have your filled 12 by 12 array of U16, that is your image. At this point, we don't have exactly clear how every tile is rotated inside this image, but this is an extra step that we can do probably next time, because I don't know if in 1 hour we can fit all of this. I hope that this is clear enough, and we can start to write some code on top of it.
Yeah, just let me recap what I understand to kind of summarize and make sure that I'm following. So just to recap the problem, basically we have tiles. We don't know exactly how they are rotated or flipped, but basically all these tiles should match to create a full picture. And they match by basically having the same border. Now, with our implementation of part 1, what we did was literally defining a list of neighbors. We defined all the possible rotations of the borders and flipping them. And we only checked wherever a cell is, we are seeing basically 2 cells with the same border, we are just putting them in a list of neighbors. So for every tile, we have a list of neighbors based on the fact that they are matching other cells through the borders that are the same. So at the end of the day, we have this hashmap where we have all the tiles, and for every tile, we have all their neighbors. And for every list of neighbor, we can have 3 different cases. If there are only 2 neighbors, that means that it's one of the 4 corners.
Yeah.
If there are 3 neighbors, that means that these are the other cells in the borders, not the corners, but the sides. And there should be like 40 of them. And then everything else should have 4 neighbors, because are all the tiles in the center. Well, in between, basically, the inside of the frame. So with that, we were able to solve part 1, because for part 1, we just needed to identify the corners. So basically, we filtered by the ones that only had 2 neighbors. And that basically was the solution of part 1. Now, for part 2, what we need to do is to actually build the entire picture. So understand how the tiles are positioned relatively to each other and how they are rotated. But for the first part of this implementation, we are not concerned too much with the rotation. We just want to understand exactly where relatively each cell is placed to each other.
Yeah, and we will come out with an array of 12 by 12 that is referencing to the tiles. So
or
like when
just
you
containing a copy of the IDs, because at the end of the day they are numbers. Like if you
Yeah,
don't
yeah.
want to
We
deal
work
with
with
references.
we can go with IDs. I put U16 and not references. We can go by ID. Likely the tiles as ID, they have IDs.
So if I understand correctly, we can pick any corner arbitrarily,
Yeah,
because at the end of the day, it doesn't matter. We will just get a different rotated or flipped view of the final
yes,
picture.
exactly.
And then from that one, we see the two neighbors, and
And we put
arbitrarily we decide which one goes to the right and which one goes to the bottom.
yes again, because if you do the other way around, you just flip the
Yeah.
image.
And then at that point, we have enough anchors to keep going, because at that point
I hope so, because for example, for part one, like we say, this is Advent of Code. The input is not evil. It's not evil,
Mhm.
so it will help us. And we just add the two neighbors, because having
Yeah.
flipped the version and stuff like that, it could have more of them. A check that we can do is filtering with tiles with 3 neighbors and see if they are 40, like you said.
Mm. Yeah, we could probably do that check as soon as we start to implement part 2,
Yeah.
because we'll need to copy most of the code from part 1 to get started.
Some
But
of
yeah.
the parsing, yes, for sure. And yeah.
Okay, so I think it's quite clear, because at that point, once we define the two anchor blocks, basically we keep going in diagonals, because when we go in diagonals, basically we have references to determine where to position the neighboring cells. And
Yeah,
at that
in
point,
the
at the end of this process, we will have all the 12 by 12 matrix with the IDs filled out. And we don't really know the rotation, but at that point,
no.
it should be easy to infer how they are rotated by looking at their position and the neighbors.
Yes,
We have Podge. Hello, Podge. Thank you for joining.
this can be done in a second step where you put also, because at the end we need to put together the real image to do the pattern matching on top of it. This is an intermediate step, so yes.
Right, so let's try to write some code.
Let's try to do this.
Okay, I'm gonna share my screen. So this was the solution for part 1. So I'm gonna brutally copy paste all of that for now. Actually, at least
But well,
here.
we need the corner, so you can even copy the filter map, but without the product. We don't want the product. We want the list of IDs of the corners.
Yeah, exactly. So let's copy all of this, and we can
But
change it later.
remember to remove the corners, because the product, sorry, not the line. Oh my god, where are
Yeah,
you?
I'll remove it in a second. So here what we want to do is not product, but it's going to be a collect as a spec of U16, did we say?
Yes, they are U16 or they are
Collect.
U16. Well,
And,
you are casting in 133, you are casting to U64, line 133.
so this will be U16. Oh, actually, we
No,
can
let's
keep.
do U16 and remove the cast, because the IDs are U16, so otherwise we are always casting back and forth and becomes a mess.
And now the other thing I want to do is, for now, I'm just going to copy paste again brutally. And we are going to call this edges.
Yeah, borders,
and
edges.
This is going to be the one with 3.
Yes.
And then we do insides or inner, whatever is the terminology. Inner tiles, I guess.
That are the one with 4 borders.
4. Okay. And now what I want to do is to do print ln of basically
the length
borders.
of the corners.
This should be 4. Then we want edges, and then we want inner. Yeah, and basically we have borders.len.
Corners. Oh, no, sorry, borders. Sorry. No, sorry.
I cannot type.
You call it borders in the string, but the variable is called corners, so I don't know. Okay.
Then we want to do edges dot len. Why len?
Do you still have the new keyboard? Yeah.
Inner tiles dot len. Now, if we run this one,
Why is complaining for the collect?
good question. Avoid using collect when not needed. Why is
It's
not needed?
Don't know.
Take the original iterator count. Oh, because it's seeing that we are only counting for now.
Yeah,
okay.
but
This
we
will
will
go
do-
away later.
Yeah, we will do stuff on top of them later. So yeah.
It is interesting that you get such sophisticated suggestions. Okay, so 4 corners, 40 edges, and 100 inner, which is what we expect, right?
Perfect.
Is the 100 correct?
Yeah,
we have...
because the total is 144.
Perfect, yeah. Then,
if you
then
sum
it's
them
good.
together, is 144. 4 corners, 4 edges, and 100 internal cells.
Okay, so that should give us confidence that there is only
one possible shape.
Matching neighbors. Basically, you only have on one border, you will have only another possible neighbor.
Yes, this is comforting.
Okay, so now we don't really need the inner tiles and the edges here, right?
The edges are useful if we put them in unset, because there is a piece of the algorithm that say when you are on the top cell, you have three neighbors, but one is the one on your left, and you have one on the bottom and one on the right to fill. And the one on the right is a border, so you have to check if that ID is a border. So keep the edges in an hash set because it's faster to. Okay, vector have contains, but I think that contains in vector is in linear time. Oh, it's an optimization we can do later. Let's not care.
Well, in any case, we are optimizing because the alternative will be that you check the 2 cells, you get the list of their neighbors, and then you count the number of neighbors. Yes. But this way we can just do it in all one.
Edges contains. It's also easy to read. Semantically is a little bit. But
so I'm gonna do this hash set. That should be enough, I guess.
I hope so. In the inner tiles, yes, we don't care. We know that if it's not a corner, and this is not an edge,
by exclusion, we don't need to collect that. Perfect.
Yeah, exactly.
Okay.
So now we can create our image array. How we mutable? Yeah.
Yes, and this is gonna be U16.
Yeah, 12 by 12.
12, and then 12.
Called.
What do we call it? Picture or
tile? No, tiles. We already use tiles. Tile map.
Tile map. I like the name. And this is equal to. How do we initialize it now?
I
guess we can initialize with 0, right?
Yeah, with zeros, because there are no tiles with ID 0. Tiles always have.
So we do this. I think that's gonna work. Is it?
That's enough.
If I put column there, yeah.
Okay, seems happy.
Okay, so now it's initially all zeros. Now we need to pick an arbitrary corner from our 4 corners. We could take the first one, for instance, and just place it at 0, 0.
0, 0, exactly. So tile map 0, 0.
So we take an arbitrary corner, first one, and we place it at 0, 0 in the tile map. So we say tile map 0. See, no, what I'm doing. 0 is equal to corners. Is it a vec?
Is a vec.
At 0 unwrap. And that will be a U16. So that should be happy with. Why it's not happy?
Because it's a
because it's a reference. Then I want an asterisk. I think it's gonna do a copy, but I mean, at the end of the day, it doesn't matter. It's a U16.
We can feed also tile map of 0, 1 and tile map of 1, 0.
Yes. Same for the two
Initial
neighbors
Yeah.
of the first corner. So what do? We consider the first one goes to the right and the second one goes to the bottom. So basically we say tile map
like we say that we don't care a lot.
0, 1 will be the right.
Okay, is the first corner, unwrap, and then dot what?
So corners. Oh yeah, we need to get the neighbors. We need to use neighbors dot 0 dot
Neighbors as a dot 0.
What is neighbors? First of all, it's an hashmap already. So we need to do get all of this.
Tile map.
Let's just call this let first corner.
Okay.
And we do first corner there. And at this point, we get a reference to first corner. And then at that point, we have a list of neighbors.
That will be true because we know.
So I'm going to do this. I know it's very verbose, but at this point, we can do neighbors of first corner 0.
Is an hash set. Hash set are indexable. Are the hash set indexable?
Good question. It seems it's working. Oh, no. Okay, fair enough. So considering that is an hash set, that's interesting. How do we...
Can you cast it to vector? Collect a vector from it?
Good question. I suppose we can do unwrap dot either dot collect into a vector. Of U16. Is that gonna make it happy?
At this point.
If I put the...
double close the angular.
Doesn't like it. Why?
Because it's a reference.
Oh, yeah. If we do into ether, because we can consume it, right? Doesn't matter. A value of type.
It's the type of the vector that is a reference. Neighbor contains a reference to U16 and not a U16.
Really?
I'm fine with, we can materialize it later. Collect as a reference, and then in line 116 and 162, 161 and 162, you put a star in front of it. Now into either.
Okay, at this point could be either because we don't need to consume it.
Okay.
Perfect. Okay, so at this point we have the first one, the second one in the first line, and the first one in the second line.
Yeah.
So we have 0, 0, 0, 1, and 1, 0.
Yes, and if we want to go for the stack version, not the recursive version, we can create a stack with just the value of tile 0, 1 and the while of tile 1, 0 in it. And also, I think we have to store also the coordinates.
Yes, you're right. So in this stack, we will have the ID and the position.
The position, because we need it for going on.
So we do what? A vec the queue. Let's call it stack. This is going to be a vec the queue of
a tuple. But if you want to declare
and a tuple is going to be U16 and then U size.
U8 and U8. Yeah, U size. Sorry, not U8. What is the usides is more handy. Why? I remember that it's more handy, but I don't remember why.
As far as I remember, uside is basically, it can change based on the architecture. So it could be either 64 or 32, depending on the architecture you are compiling for. And then that's why it's used for indexing. So it's kind of, whatever is the indexing size. Basically.
You stick to the native architecture of your CPU, so it's faster for the architecture itself to do that. Okay.
So now we have a stack.
Pushing
and in the stack, we need to push front or push back?
We have to pop from one side and push in the other. So choose one. I would
what
say,
is more natural to you?
To me, it's more natural to pop from the front, and push in the back.
Okay.
That sounds terrible, but 0, 1 with coordinates. Now you also have to put the coordinates. No, the coordinates.
Yes, and this. I wonder if this needs to be a reference or it's gonna copy it. Probably it's gonna copy it. And the coordinates are gonna be 0, 1.
And we have to do the same for the other.
Yeah, it's gonna do a clone there. Okay, or a copy, whatever is the right terminology. And now 1, 0, 1, 0.
Okay. From here, we start with our loop until we have stuff in the stack, or we know that we have to do.
Stack is empty.
Well, it's not empty. Okay. Otherwise, we exit and we do nothing. Here, we have to pop from the front 3 values, the tile.
Tile ID.
Tile ID.
X and Y.
Yeah, X and Y, Y and X. As we say, it make no sense. We don't care.
Stack.pop front unwrap.
But it's guarded by is empty. You need the unwrap?
Yes, because pop front returns an option.
Okay. Because we know that it's not
empty. We know we can unwrap without exploding for sure.
Yeah.
But we need to unwrap because we get an option.
Okay, cool.
Now is the beautiful business logic with all the edge cases.
Yes, let's start. We are a border. We take all our neighbors. We can take the neighbors from the neighbors hashmap, right?
Yes, and we have the tile ID to decide.
So we take our neighbors.
So let's do that. Let neighbors. Do we want to do again the vec trick? I guess
we have to remove from this. Can be an hash set, can be a vector. In the end, what I want is having only one element every time, so we know for sure what to put in a place. So I don't know if keeping with the hash set or going to the vector. In the end, it's a vector of 3 elements, so it's not a vector that is impossible to handle. 3 or 4 elements, but yeah, very small element. Go with the vector. Copy what you have in line 156.
Okay, so 156. Yeah, we do neighbors.
Change the name of the variable to local neighbors, because otherwise you are ghosting, shadowing, not ghosting.
You're right. Yeah, and then we have problems. Calm down. Get tile ID, and then we do unwrap because we are sure that exists, and now we have an hash set of U16, right?
Okay. Is copied or is a reference? Because
this is a reference.
Okay, let's see. Probably we have to remove from this. But well, we can remove from this because at this point we don't need it anymore after this step. But let's see. Let's try to remove from it. See if it explodes.
Otherwise, we can do a clone and
also
make
this must
it
be
mutable.
Yeah. But well.
So if we do this and we do dot clone into, I guess, is that gonna work?
Why clone into? Clone nothing else is not working?
Oh no, clone. Yeah, you're right. Okay.
Seems to work. Okay, now we have to remove from this list of neighbors the neighbors that are near us. So
That we already found.
yes, so we always know that there are the one on the left and the one on the top that we already have.
Either we have or either there is no cell in that position, right?
If there is no cell in that position, we don't remove anything.
Yeah, so basically what I'm saying, if either top or left are going outside the main picture, it's like if we have a border, basically.
Yeah, we don't care. We don't remove,
Okay.
obviously, because there is no neighbors on top if we are the top one.
So how do we write this?
Okay, let's try like this. If our y is greater than 0, we remove from local neighbors the cell that is at tile map of our x y minus 1.
So we do, is there a remove? Yes, of
Tile map
tile map
of x of y minus 1. Obviously, we can do this only if we don't go negative, because and the if is to guard the negative side. If there is not this value that it
Is
can
this
be,
gonna work? I think we need a reference to that.
Okay.
Okay, it likes that. Similarly, we can do the same for x.
For x,
right?
yeah, but only if x is not.
And we need to remove x minus 1 and y.
We have to do the same for when we are in an inner cell. We have to do the same for the one at our right, so at our x plus 1. But we have to do that only if we are not on the right border. So if x is less than 0, 11, okay. If x is less than 11, that we already have.
Already placed. Now, sorry, say again.
If our x is less than 11, because we know that we are 12 by 12, we are coding 12 is something that code. So if we are less than 11,
11, yes,
and tile map of x plus 1 y
x
plus
1
and y is not 0, because we initialize everything with 0. It can be that is if it's not 0, we remove that cell from our neighbors. Okay.
That cell means
Tile map x plus 1 y, the one that is in the if.
Yes, okay, with a reference.
Oh yeah, okay.
And we need to do the same with
the one below. We could do the same, but we know that is always missing because we are always going in diagonal from the top. But you can do that just to be sure. If y is less than 11 and tile map of the same, just changing y with x with y. Plus 1, not 0.
And we do all of this.
At this point,
we hope we have only one.
We can have 2 or 1 neighbors. If we have 2 neighbors, it means that we are on the top row. If we are on the top row, the one to our right must be a border.
One of the corners,
must be the other. If there is only one cell, we put the one cell in the only empty cell that we have around us. That is probably the one below us, but let's say that we check. But I'm quite sure that will be the one below us. But
so basically, if local neighbors.
Let's do the length 2 before. If it's 2, or is 1. If it's 2, we have to detect which one go on the right and which one go on the bottom. Okay. So we have to count the number of neighbors of.
If we have 2 neighbors left,
we need to decide where to put them.
And below.
And below, yeah. Okay, here we can have an edge case if we are on the top and then one at our right is a corner. But we are addressing this. Here we have to do for all the local neighbors. Of what is of
JavaScript.
JavaScript, okay. So if the neighbor is a corner or a border.
So neighbor, so corners
contains
or includes? What
contains.
do we have?
I think it's I saw contains when you were the third, n or the variable I was called we created, and I don't remember the name. Edges. N. There is n.
No, wait. This is corners. If corners
n contains
n, yeah.
or edges contains n, it goes on the right. So
that basically means that tile map.
Yeah, sorry, you're right. Tile map.
Tile map of
x plus 1 y
of y,
that is our right, is equal to n.
Is equal to
n.
n.
Else it means that is the one below us. Because if it doesn't go on the right, it goes below.
Okay.
Here, if we are on the bottom row, here if we are on the bottom row, we will never reach this point in theory. So it's fine to do the +1 without checking that y is less than 11. I think we are not, but well, if we have an exception, we fix it. At this point, we have to put in the stack all the cell that we added. So every time we add to the tile map, we have to add also to the stack.
Yes.
So in 190, we have to do stack dot insert append. No, pushback. We say the pushback. And there will be the tile map of n, because we know that is n.
So n, then
x plus 1 and y. And in the other
I wonder
side,
if it's going to complain. No, it's going to do a copy. Cool.
Okay, accepted. Here
now this
n,
one is going to be x.
n plus 1. Okay, when we are on the right side of the moon, it will just put the one below. Yeah, probably.
Now the question if this one is 1.
Yeah, sorry, we have to do that case. Yeah, sorry, forgot. If that one is 1, it goes below.
So we do else if local neighbors.len
is 1.
Probably we can do a match statement, but we will refactor
we
later.
can do that later.
So at this point, basically, we do tile map.
Yeah, you can copy 193 and 944.
This one, yes.
Yeah, but n is the only element of our local neighbors, so
that will be
let n equal to the only element we have there. local neighbors.
Oh yeah, how do we local neighbors dot
first? Only one. I don't know. I want the only element in this stuff.
First.
No.
Next.
There is one element.
Come on, that should work.
Ether, nest, unwrap, everything. Yay!
It needs to be.
Okay. Do you want to debug tile map after this? We see if we explode and what we have.
So here we have
after the loop. No, with this loop we are fine. After this loop we have tile map, right? Then we have to work inside it, flip and create the real image. But right now we have.
Do you want to print basically?
Yeah, I want to see what we have there, and also I want to see if our code is exploding with some indexes outside of bound. I'm not.
Let's see what we get.
Yes.
Explodes.
Okay. Where?
Index out of bounds. The len is 12, but the index is 12. Line 190. 190. There. So oh yeah. X and Y. Do we need to swap them?
Why?
Because you have matrix where. Sorry, let me.
No. You're right. The first index is in our mind what normally is the Y, because
the usual mistake I always do.
But it's not important, because what we have out of here is flipped version of it, and we don't care about the flipped version. As easy if you are consistent with keeping the first X and the second Y.
Well, it doesn't matter, but we are considering right and bottom. At that point, it matters, right? For our reasoning to be correct.
No, I don't think it matters. But well, the index there, I think, is a problem of why we got there with an X that is 11, and so we made the 12 and 2 neighbors. If you want to swap them, I'm fine.
I'm going to swap all of them just because at that point the reasoning is correct, right?
Yeah. But remember,
so let's start from the beginning. Like this one is 100% sure.
0.
That's easy. Now this one, what we want to say is the right one.
But
so that will be.
We don't care because.
Just to follow the reasoning consistently. So let's just say that this one needs to be the right one. What are the indices?
0,
it's going to be row 0, column 1.
Yeah, that is the right one.
You know what? I'm going to be calling this row and column.
Right, okay.
Rename. Okay, now it should be easier to refactor this because.
But now it's like you want, row and column.
Right.
Now let's go down to our stuff. Okay. Now you have to refactor if you want row of row and column +1 to go to the right.
In which line?
190.
Okay.
That is just a row.
So this is going down rather than going. Yes. Okay. Now this one needs to go to the right. Okay, that's
and
the
also
issue.
In line 91, you have to fix it.
And this.
Now, why is complaining now?
I don't know.
What we changed it to be so.
What?
Okay, it's the same as else, but we have to change the else.
Oh, okay. Yes, of course. Thank you, Clippy, but calm down for a second.
Yeah, give us time to write code.
I mean, it's very cool that we get this suggestion, but yeah, give us a second. Cool. Okay, so that makes a little bit more sense now. Do you think that's enough? No, this one.
199, we have to populate the one below. So it's row plus
So
one.
row plus one
and column.
And column. And the same,
the same in the stack push. Now let's see what's happening if we still have the out of bound or if this fixed. I'm not sure. No, we still have it.
Still
we have
issues.
we have to reason about it a moment. 193 now. Let's scroll to
193. So it's in a different position now.
Yeah. Okay, what's happening here? Here we have two neighbors. Okay.
So this is probably the last line.
If the neighbor is not a corner and is not an edge. If the neighbor is not a column, is not a corner, sorry, and is not an edge.
I want to see if we are in the last line before exploding.
You have the ID. You have to print the coordinates.
So row is 2, column is 11. So we are at the very last column of the third row. And what we are trying to do is to go at 12. Why is that?
Go to where we remove neighbors a moment.
Where we remove the neighbors here.
Or we are saying remove the neighbor on my left or column left if there is one.
So we need to change all of these ones as well.
That's the reason. The one on the left, we remove it. Cool. We remove the one above if we have it. We remove the one below if we have it, and we remove the one on the right if we have it. We are removing 4 neighbors at maximum if we have them, right? Checking the borders to just avoid to go out of bound, correct? Okay, let me do something. Let me do debug local neighbors before where you are debugging stuff.
What do you mean?
Line 172, for example. 172.
172.
The DBG local neighbors.
Before all this stuff.
Before removing them, and DBG them after removing them.
Okay, so what?
Debug a reference to it because it's consuming the local neighbors.
Really? That's stupid.
Yeah, it's for some reason was consuming them.
Whatever. Okay, so if we rerun, we should be able to see
what's happening. Yeah. Okay. Local neighbors before exploding is 2819 and 1129 and 2757. And it gives back 2 of them. But our current coordinates are...
Why is it not showing them anymore? Did I remove it? I have it here. So now is it exploding in a different place? 192. Oh, now it's exploding here again. Why?
Sorry,
what did we change?
We changed we debugged stuff. I don't care. Put the debug also there. This is strange, guys. Again, we are in.
Now it's exploding 203, which is this one.
We are putting the bug, and the debugger is changing where it crashed.
And also the local neighbors is different now.
Sorry.
The only thing I could think about is that maybe the order of the set changes.
the order in the hash set is not fixed, but the content must be the same or not.
But we take arbitrary values just to start from that hash set.
I also, based on the corner you start from, you have different errors. Could be. Okay, let's put the bug also there. At this point, with the bug in all the places where we crash, and
so we put the bug here, right?
yes. Here is complaining that row +1 is exploding when we have only one. Okay. Do something there. If we land there again. We have row and column. We have our only neighbors. Can you debug or print all the tile map cells around us? But well, no, let's do that later. Let's try it again with this. Okay, now we know where we are.
Now index out of bound, the line is 12, but the index is 12. 193, which is here.
Okay, we are there. Our row and our column. We went out of bound with the column because it's 11, and we went to 12, and it exploded. We have 2 neighbors left. So we are we have 2 neighbors to fit. So the one on the left was not removed. Go where we remove the neighbors on the left.
Should be this one, right?
Row is less than, okay, if column is more than 0, and it is because it's 11, tile map row of column -1 remove from the neighbors. Cool. Can you debug that value? Tile
Is
map
this
row
one
column.
returning? Yeah, this one is returning true or false.
Based on what?
If it's removing it or not. I suppose if it's not finding it, it will return false.
Debug me the value of tile map, the value that we are trying to remove.
Oh, I see. In here, right?
Yeah.
dbg of
that, because seems to me that in the cell we don't have a neighbor at this point. So we started with 4 neighbors.
0.
Oh, this is a problem. Why is that 0? That must, or we are in an inner cell that is 11.4, but 11.4 has 4 neighbors. This is wrong. Row 11 is the bottom row, right?
Row 11 is the bottom row, yes. And why position 4?
Position 4 is just this one. Column 4 is one of the cell on the bottom. It must be a border, but here it is an inner cell for some reason. Because it has 4 neighbors, you see? The original neighbors are 4, not 3. If we are in the last line must only contain cells that have 3.
Is it maybe the way we populate the stack?
I was thinking about it.
Because what we want to do is we always want to look what the top one first and then the bottom one, or vice versa.
We look the one on the right. But sorry, we made a mistake. Probably scroll a little bit. if we have two neighbors, one goes on the right and one goes on the bottom right, but the one that goes on the right is the one that must be a border or a corner, only if we are a border.
Okay, so how do we define that?
The condition in line 192, but oh no, my God, I have to think on top of this. Okay, we are at a 1 hour mark. What do we want to do? We think of this for the next time and we wrap it up here, or we want to go down the rabbit hole?
No, we could stop here and we could see next time. Maybe if we have time during the week, we can try to get to the point where we have a
This is
working
working.
version of this.
Yeah.
So that next time, what we want to do is basically, once we have all the IDs in the right position, we just
Yeah.
need to figure out how they are rotated or flipped. And at that point, we have the full image. And
Yes.
then the rest of the problem, there is still a lot to do because we need to remove all the borders, create a real picture,
that
and
will
then
be
look for the snake patterns.
That will not be 10 by 12
Will
by
be probably
12.
100 by 100, right?
We have to remove the matching borders. So every tile is 9 by 9 in reality that we have to put together plus 1. So is 9 by 12 plus 1 by 9 by 12 plus 1. So yeah, okay. Strange numbers. Of sharpened dots.
Isn't gonna be 100 by 100? Anyway, we will do the math.
I can do the math if you want. By 9 plus 1. I think it will be 109, but by 109.
Okay.
Because you have 12 cell by 10, that is 1 and 20, but you have to remove 11 matching borders, because between 12 tiles you have 11 match borders, right? And 120 minus 11 is 109.
Oh, right, because we need to keep the outer borders. Yes,
yeah,
right,
the outer borders are important.
I didn't realize that. I was thinking we just remove the border out from every tile. No, you need to remove only the inner borders. Yeah, fair enough.
Yeah, the outer borders, I think they're still needed. Yes, here in theory is working. Can be how we populate the stack, but like Luciano said, I think we have to make a pull request to ourselves or having it working, and then we can go on from there. Sorry for this, but this is a very tricky array manipulation stuff, and we trust that we are not comfortable manipulating arrays yet.
Yeah, I think it will also be nice to try to come up with pictures of all the cases. So next time we can explain better how the code represents every scenario that we could get from, when we try to match the different neighbors.
Yeah, exactly.
Because I'm sure we are doing some silly mistake in one of those cases.
Yes, because we are considering an inner tile as a border, and this must never happen. Okay, let's wrap it up. You can find the recording, the embarrassing recording on YouTube. The link is in our Twitch section. If you're watching this on YouTube, we do live streaming every Monday, 5 p.m. UTC, 6 p.m. Dublin time. Make sure to check the Twitch link in the YouTube description and give us a follow and thumb up and everything else. Feel free to leave a comment, open PRs. The repository code is again on GitHub.
Which I have to find the banner there.
That is this one. Everything is accepted. We are trying to learn Rust. Don't expect our solution to be perfect. This time, don't even expect them to be working. We are writing code that is not very idiomatic. We have pull requests that are. So look at what we have merged, because if we have a good PR, that means we normally merge it. If you know better ways of doing them, please tell us. Thank you for the suggestion. Thank you for the people that was in the chat. Are we going to write somebody?
We have one viewer, so I guess we are going to skip it for today.
Let's skip right for today. Thank you and see you next time.
Bye.
Bye.